Welcome to this exciting lecture on endocrinology. Today, we are going to explore the fascinating microscopic world of the thyroid gland. We will discover how its unique cellular architecture allows it to act as the body's ultimate metabolic factory, storing months' worth of vital hormones. By the end of this session, you will understand exactly how form meets function in this incredible organ. Let us begin by visualizing the thyroid gland not as a single solid organ, but as a massive, bustling factory. Imagine looking down from a bird's eye view and seeing millions of tiny, fluid-filled balloons. In the human body, each of these microscopic balloons represents a follicle, which is the fundamental working unit of the thyroid gland. This unique balloon-like setup is incredibly important because it allows your body to stockpile months' worth of raw materials and finished products. This ensures you never run out of metabolic energy, even if your diet temporarily lacks essential nutrients. Now that we understand the factory analogy, let us look closer at the structure of these individual balloons. Histologically, each thyroid follicle is lined by a single, continuous layer of epithelial cells, known as follicular cells or thyrocytes. Think of these as the living worker cells forming the rubber skin of the balloon. They rest upon a thin basement membrane, separating them from surrounding blood capillaries. The hollow center of this follicle, called the lumen, is completely filled with a thick, gel-like substance called colloid. This colloid is primarily made of a massive glycoprotein called thyroglobulin, which serves as the storage form of thyroid hormones. While the follicles are the main attraction, we must not forget the spaces between them. Nestled in the connective tissue spaces between these spherical follicles are another group of cells called the parafollicular cells, or C cells. These cells have a completely different job from the follicular cells. Instead of managing metabolism, they secrete a distinct hormone called calcitonin. Calcitonin plays a crucial role in helping to regulate your blood calcium levels. So within this one gland, we have two entirely different endocrine functions happening side by side, perfectly organized at the microscopic level. Understanding this microscopic structure is absolutely critical because the histology directly reveals the health status of the gland. The thyroid is unique. It is the only endocrine gland that stores its products extracellularly, outside the cells. In a clinical setting, a doctor can look at a biopsy and instantly gauge the gland's activity just by the shape of the follicular cells. If the cells are flat and squamous, the gland is resting. But if they are tall and columnar, the gland is working in overdrive to pump out hormones. This simple visual check is the gold standard for diagnosing devastating conditions like Graves' disease. To truly appreciate how the shape of these cells affects storage capacity, we can model a single thyroid follicle as a perfect geometric sphere. This brings us to our first formula. The total volume of the follicle, V total, equals 4/3 pi times the outer radius cubed. Conceptually, this represents the absolute boundary of our microscopic factory. The outer radius is measured from the very center of the colloid all the way to the outer edge of the cells resting on the basement membrane. Because the radius is cubed, this formula tells us that if the outer radius doubles, the total volume increases by a massive factor of 8. This shows how rapidly a follicle can expand when stimulated. Now that we have the total volume, let us look at the storage pool inside. The volume of the colloid is calculated using the exact same spherical geometry, but this time we use the inner radius. V colloid equals 4/3 pi times the inner radius cubed. The inner radius is the distance from the center of the follicle just to the inner edge of the follicular cells touching the colloid. This represents the actual storage capacity of the follicle. When the thyroid gland becomes highly active, the cells consume this colloid to release hormones into the blood. As they do this, the inner radius decreases, which physically shrinks the total volume of the stored colloid. Before we move on to the cells themselves, let us see this colloid formula in action with a concrete example. We are given a healthy, resting thyroid follicle with an inner radius of 50 micrometers. We are asked to calculate the total volume of the colloid stored inside. We start by plugging the inner radius of 50 directly into our spherical volume equation. Cubing 50 gives us 125,000. We then multiply this large number by 4/3 and the constant pi to account for the spherical geometry. The final answer is approximately 523,598 cubic micrometers. This massive number physically demonstrates why even a single microscopic follicle is incredibly efficient at storing dense, hormone-rich protein. This brings us to an important question. How much space do the actual living cells take up? To find the volume of the cellular shell surrounding the colloid, we use a simple subtraction. The volume of the cells equals the total volume of the follicle minus the volume of the colloid. Conceptually, we are taking the entire balloon and hollowing out the fluid inside, leaving only the rubber skin. When the thyroid is overstimulated, the cells grow taller, changing from cuboidal to columnar. This physical growth increases the cellular volume, while simultaneously depleting the stored colloid volume, as hormones are rapidly produced and secreted. Now that we have all our formulas, let us analyze a highly active follicle from a patient with Graves' disease. We are given an outer radius of 60 micrometers and an inner radius of 40 micrometers. The cells have grown tall and columnar. First, we calculate the total volume using the outer radius, which gives us roughly 904,000 cubic micrometers. Next, we calculate the depleted colloid pool using the inner radius, yielding about 268,000 cubic micrometers. Finally, we subtract the colloid volume from the total volume. The final answer shows the cells themselves take up 636,696 cubic micrometers. This perfectly illustrates the histological reality. The worker cells have massively hypertrophied to produce more hormones, while the storage pool has shrunk. Let us bring all these concepts and calculations together visually. What you are looking at is a cross-section of a single thyroid follicle. Notice the large pink central area? That is the colloid, packed with thyroglobulin. The arrow labeled R inner shows the radius of just this storage pool. Surrounding the colloid is the ring of purple follicular cells. The arrow labeled R outer extends all the way to the basement membrane, representing the total size of the follicle. Just outside the follicle, you can see the blood capillaries waiting to transport hormones, and the separate parafollicular C cells nestled in the connective tissue. This diagram beautifully summarizes how form perfectly matches function in the human body. We have covered a lot of ground today, so let us review the key takeaways. First, the thyroid gland is uniquely organized into millions of spherical follicles, acting as microscopic factories that store hormones extracellularly in the colloid. Second, we learned that follicular cells manage metabolism, while the parafollicular C cells regulate calcium. Third, the physical shape of these cells, whether flat and resting or tall and active, directly indicates the gland's health and activity level. Finally, by using simple spherical geometry, we can mathematically model these changes, perfectly linking microscopic anatomy to physiological function. You now have a solid understanding of thyroid gland histology. Great job!